Swayam Prabha. Digital India. Educated India.
In this lecture, we will discuss about the features or the parameters or the properties which can be derived from protein sequences. In the last class, what did we discuss? Phylogenetic tree construction, right? What is a tree? It will give a representation of relationships, right? So, you can give the relationship among different sequences, right? For example, we use the protein sequence or the DNA sequence, and also we try to see the time, right, to evolve from one sequence to another sequence. So, the different ways to construct phylogenetic trees, right? What is the very commonly used method to construct phylogenetic trees? EPGMA method, right? We also discussed to construct a tree for a given set of sequences. We used 5 different sequences, right, and we constructed a tree, right. So, in this case A and C are common to each other and D and D are common to each other, right, and then B and AC are common to each other. We construct a tree and accordingly we assign weights. It may also be possible to add another one internal node, right, AC comma B, right, at this point, and you can recalculate the weights. Then what are other methods we discussed for the tree construction? Neighbor joining methods and maximum likelihood methods and so on. Then we discussed about a program which can be used to construct trees. So, what is the name of the program? Phylib. What is input for the phylib? That is multiple sequence alignment, right. You can use mapped to get the multiple sequence alignment. You can directly give this input in phylib and you can get the trees, right. Then we discussed about the bootstrapping, okay, that is one of the methods to assess the performance of this method as well as significance, right, by making several sets of random sampling. So, in this lecture we mainly focus on the protein sequence analysis, right. Where shall we get the sequence? In UniProt database, right. So, I show a sequence. This is for the hemoglobin A chain from bovine. So, and this is the amino acid sequence, right. I give the amino acid sequence in single letter code, right. You are all familiar with the single letter code and 3 letter codes, right. So, here I use mainly single letter codes for each amino acid residue. So, you have the sequence. So, what can we do with the sequence? What are the information you can derive from the sequence? So, look at the sequence, it is the combination of different amino acid residues in a specific combinations, right, sequence. So, whether any differences or similarities among different sequences in UniProt database. If there are similarities or if there are differences, whether we are able to use these differences to infer the function or to infer the 3D structures or to infer any binding sites and so on. Right, now we have the sequence, right. There are various parameters you can calculate. What are the easiest parameter you can calculate from an amino acid sequence? The frequency of occurrence, right. So, easily you can count how many times A present, how many D's, how many C's and so on. So, here for example, if I show a peptide, okay, this is not a real sequence, this is a peptide, right. So, if I give this one, you can easily count the number of times each amino acid residue occur in this particular peptide. So, how many times A present in this peptide? There is only once, okay, A is A present once. How many times E? Twice, right. So, one here and one here, 2 E's, right. So, if you given any sequence, you can get this number, right, and then see whether this number resembles anything, right. We will discuss about that. So, now this is a real amino acid sequence, right, this is a protein. So, here if you see this amino acid sequence, so how many times A occurs in this sequence? 15 times A occurs, right. If you look into this occurrence of different amino acid residues, some amino acids occur very frequently or very more time. For what are other amino acids which have high preference, high occurrence? Leucine 18 times, valine 18 times. So, these are the amino acids which occur very frequently in protein sequences, right. So, there are some amino acids, right, which are rarely occurring. For example, if you see cysteine only 2 times, tryptophan 2 times, for this case methionine also 2 times, right. So, if you consider several sequences, you can see the variation in the patterns. For this particular sequence, okay, for mainly the hydrophobic residues alanine, leucine, valine, right, they occur predominantly, that 15 times and 18 times in this sequence, right, you can use this information. For example, if you have 2 sequences, one with the short sequence, one with the long length, for example, one with 100 residues, one with 1000 residues. So, how far these occurrence vary? For the small sequence, we get less numbers, right, because only 100 residues. If it is 1000 residues in a sequence, then the numbers will be high, at least 10 times, because the length is more. So, directly if you compare these 2 residues, right, what will happen? Naturally, the longer ones have more number of amino acid residues. To normalize this, so right, you have to directly compare, then we need to normalize with something, right. What is the factor we need to normalize in this case? Length, because first case 100 residues and the second one is 1000 residues. So, if you normalize with the length, then you can see whether any preference of amino acid residues in any particular protein of different lengths. So, in this case we use the term composition, right. So, composition gives you the normalized value of amino acid occurrence. So, essentially this is the number of amino acids of each type, this is called occurrence, right, this we call as occurrence, and divided by total number of residues n, right. So, we can define amino acid composition as composition of I, this is equal to sigma n of I into 100 divided by n, right. This is equal to I, n I means for each type of I you have to count how many times I. So, you can see, for example, you take single residue, you can also see n of I multiplied by 100 if you get the percentage and divided by n for any specific residue I. For example, alanine, composition of alanine equal to number of alanine in the whole sequence divided by n, right. If you want the percentage, you can put multiplied by 100. So, here I stands for the 20 different residues, right. For each residue one alanine, aspartic acid and valine. So, you will get for 20 different residues. So, n is the total number of residues which we use for normalizing the occurrence, right. Summation you can do it for all the residues, but if you take the total, that will be 100 percentage, right. If you take the total, you will get the 100 percentage. So, you can take the composition of alanine, which you can calculate it as 15 residues, for example, into 100 divided by 147, that is equal to 10.2, right. This is if I take this example, here how many alanines in this protein? 15. So, 15 divided by 147, right, if there are 147 residues multiplied by 100. What is the composition of valine? 18 divided by 147 multiplied by 100, right. We will get the composition of any specific residue in this protein. If this is the case, if there are 100 residues in a protein and 1000 residues in a protein, right, you will get the composition and the total will be 100, right. So, even the 100 residues present or 1000 residues present, when you normalize with the chain length, you will get total value 100. In this case, you can directly compare the composition of each amino acid residues, right. Even is 15 or another one is 150, so you can compare when you normalize with the chain length. So, this will give you some information other than rather than the just comparing the occurrence. Then how to write a program, how to calculate the composition if I give any sequence, right. For example, I have a sequence like this, so I want to calculate the composition. What are the input we require? Sequence. We need a sequence, this is the sequence we require. Then what else we need? List of amino acids we require, right. How many amino acids? 20, right. So, if you represent the sequence in single letter code, right. So, we have to list the amino acid residues in a single letter code, right. This is because then only we can easily match. Okay, now we can have the 20 residues. So, we have the sequence, then we need to get the occurrence first. For getting the occurrence, before we count, first we need to normalize, right. For the 20 residues, we need to normalize all the numbers into 0. So, in the initially we can now we can see that number of alanine equal to 0, number of aspartic acid equal to 0, for all the cases we put 0. Now, what we have to do? We have to count, we have to compare. Take the sequence first, for example, this is A, you have to compare this A with the list of amino acids. Okay, here you can see the list of amino acids. If you compare this and this, if it matches, then we add in this array number of A equal to 1. Second one, if you take I, it matches A, it will not match, it goes on the 20 residues, when you have I, it will match. So, when you pass all the amino acid residues in the sequence, so where you have match, then you can count. So, now we have the numbers for all the 20 residues, this will give you the amino acid occurrence. So, now we have 20 numbers for the 20 amino acids, right, as an occurrence. So, now we have the occurrence. Now, what do I have to do? Right. So, we have the occurrence for each 20 residues, then normalize with the number of residues. Take each residues, right, 1 to 20, normalize with n for each case, then we get the composition. If you want to get the composition in percentage, then you have to multiply this with 100, right, very simple. So, we take the sequence and get the 20 different amino acids and do the matching. If it matches, then increase the number as plus 1, right, because already we initialized, then complete it till the end of the sequence, right. Then we have 20 numbers for the 20 amino acids, then normalize with the n, so then we will get the composition, right. This is easily you can calculate the composition. So, now I give an example, I have a sequence, okay, this is amino acid sequence, how to get the composition. So, here we have 20 residues, we compare with these residues and then we can find the number of residues in each 20 residues. For example, if you see how many times G occurs, 5, 1, 2, 3, 4, 5, right, G occurs 5 times, D 2 times, right. For 20 residues, right, we have the values for the 20 residues. If you add up everything, you will get 79. This is occurrence, right. To get the composition, what do you have to do? You have divide by n. So, for each case you normalize with the n. What is n here? 79. N equal to 79, right. So, we divide with the 79, then you will get this number and multiply by 100, you will get in percentage. So, now if you have set of sequence, if I give, you can calculate, right, you can calculate the occurrence as well as you can calculate the composition. So, you can also write a program and this same information you can also obtain from different resources, right, several software available in the literature, just you give the amino acid sequence, right, then you can get the composition occurrence. So, one of the software you can see is PIR, already discussed earlier. What is PIR? Protein information resource, right. So, what is mainly is developed for what? Sequence database, right, they collected the information or amino acid sequences and they developed database for sequences, and when they make a database, it is very important to do some analysis and to get some information, otherwise adding up the data one by one, many data, it will not make any sense. So, we need to analyze the data and we have to extract some information which are hidden in the sequences, right. So, they developed several tools, you can search with the text, you can search with the blast, you can search with the composition or anything you can calculate. So, if you want to take the calculate, go with this analysis. If you see a list of tools available and here you can see the tool which can calculate the composition. So, go click on this composition and you get this window, either you give the uniprot identifier or you can give your sequence. So, if you give this your amino acid sequence, right. So, you insert your amino acid in the single letter code, right, okay, you can give a single letter code, right. So, then if you click on submit, you will get the sequence, okay, this is your input, okay, here this is your sequence occurrence as well as the composition. So, you have 20 amino acid residues here. So, as I showed earlier, alanine occurs 15 times and the composition is 10.2%. So, you get the sequence in the x axis and y axis you can get the composition, right. For any sequence, just you paste the sequence and you get the data. Then the next one you can calculate the molecular weight, the simplest one. So, how to get the molecular weight? So, because if you have the dipeptide, for example, if you have one amino acid and two amino acids, three amino acids, right? If you join together by means of peptide bond, when you make a peptide bond, so will by the elimination of water molecule, right? So, in this case, when you combine amino acid two residues, you will eliminate one water molecule, right? If there are n residues, how many water molecule will eliminate? N minus 1 water molecule you will eliminate. So, in this case, if you want to calculate the molecular weight, right, in a sequence, for each residue we know the molecular weight. For example, alanine is 89 and glutamic acid 147 or methionine 149, tryptophan 204 and so on. We know the values. So, if we have a sequence, for example, this is a sequence. So, to calculate the molecular weight, right, what we have to do? First, we have to assign values for each of the residues. So, how many alanines here? 3. So, 3 multiplied by 89. Then, what I is 1 time, 1 multiplied by 131 and 1 T, this multiplied by 119. So, this equal to 267, 131, 119. So, total will be 517, right. So, this is the molecular weight? No, right, because this is the molecular weight of these 5 amino acid residues, but when you combine 5 amino acid residues, we will eliminate 4 water molecules, right. So, you have to subtract 4 multiplied by 18. What is 4 multiplied by 18? 72. So, now the answer will be 517 minus 72, this equal to 445. So, if you have any sequence, you can calculate the composition occurrence and you can do the molecular weight. If you have the occurrence, you can use the occurrence to get n of I. So, multiply it with the weight for each residue W of I. So, this will give you the full sequence. When forming the sequence, you will eliminate n minus 1 water molecules. So, you subtract with the 18 into n minus 1, 18 is the molecular weight for water, right, then we get the molecular weight of that particular protein, fine. Because I have a sequence, okay, now I give a sequence, the same sequence I give, right. What information do you need to calculate the molecular weight? Sequence we need, and then we need 20 residues. If you have 20 residues on the sequence, you can calculate the occurrence. So, when you get the occurrence, then what to do? Multiply by weight. So, for 20 residues, we have the weight, right. So, W of I. So, N of I we have, right, you can calculate, already we got the occurrence. So, for each occurrence, you multiply by weight of I and you get the summation. Summation equal to I equal to 1 to 20. So, you get the weight, then you have to subtract with the minus 18 into n minus 1, right. So, we get the 4 G's and 2 D's and so on, multiply with the appropriate weights and subtract with 18 into n minus 1. So, we could do this, we will get this number. So, how to calculate the molecular weight? Right, we need the occurrence. So, we get the occurrence, we know the values for each amino acid residues, the molecular weights, right. So, we calculate the N of I multiplied by W of I, right, and you have to subtract the molecular weight of the water, right, this is equal to 18 into n minus 1. So, if you assign the values for all the residues and then calculate, and finally you get the number 8129. Now, you can calculate the average properties, right, just we get the composition and occurrence and the molecular weight. If we have the occurrence, it is influenced with various properties. For example, if you have more number of charged residues like aspartic acid or glutamic acid or lysine or arginine, you can say the protein is highly charged, right, whether it is acidic or it is basic. If you have more number of hydrophobic residues, then you can say this protein A is highly hydrophobic than protein B, right. If you compare different sequences, you can use various properties of the individual amino acids, right, and use this value to get the average values for the whole protein, and this will tell you whether the protein is based on any property, it is high or low. For example, if you have sequence 1 and sequence 2 AIKT, here RSTV, how far these sequences behave based on hydrophobicity. So, you can put here again VA and TS. And if you see this sequence number 1, so we have values for the 20 residues, right. So, for example, if you have hydrophobicity, 20 different amino acid residues, they have 20 different values, or polarity, or charge, right, or tendency to form hydrogen bonds, which residues have higher tendency to form hydrogen bonds. Among the 20, if it is a polar residues, they have high preference to form hydrogen bonds, right. Likewise, 20 residues, they have 20 values. How far the residues are flexible? Some residues are highly flexible, some residues are rigid, right. How many rotatable bonds each residues can have, right. Likewise, there are various properties, right, for each amino acid residues. So, if you have the values, then sum of the numbers in a full sequence, that will tell you the characteristic features of the complete protein, right, based on the particular property. For example, if I have sequence 1 and sequence 2, right, and I want to see which residue is highly hydrophobic. So, if you see I have values for 20 residues, I give one example. For example, I classify the amino acids into 4 groups, right. One is hydrophobic, which is highly hydrophobic, and one is polar and one is charged. For the hydrophobic ones, I put 1, which is highly hydrophobic like isoleucine, leucine, valine, tryptophan, I put 2. For the charged ones, I put -2, and the polar ones I put -1. If this is the case, what is the value for sequence 1? A is equal to 1 plus I equal to 2, K equal to -2, T equal to -1, B equal to 2, A equal to 1. So, this equal to 3, -3 0, this equal to 3. If it is second one, what is second sequence? R equal to -2, -1, -1, plus 2, -1, -1, this equal to -4. So, compare these two sequences, you can see first one is highly hydrophobic, right, than the second one, right. So, if you have any protein sequence, right, you can calculate different properties. Here I give the numbers 1, 2, -2, -1, but we have the actual values for the 20 amino acid residues, which can be obtained by experiments, either octanol water experiments or the ethanol water experiments by getting the relative solubilities, or computationally derived scales. There are several computationally calculated values for the 20 amino acid residues. We can use exact values to see the average property of any protein. So, I have the two sequences now. You can calculate the values, right, using this equation. What is N of I?
Composition.
N of I is the occurrence of each residues, right, occurrence of each residues. Hb of I, that means this is the hydrophobicity of residue I, right, hydrophobicity. To get the average, you have to normalize with N. What is N? Number of residues, right. So, if you take this equation, so how many A is here? Number of A equal to 1, M 2, then what else? E 1, N 2, L 1, D 1, S 1, R 1. So, we group the numbers, right, if you see back, right, N P Q S T, right, S N, that is equal to -1. So, -2 plus -1 -3, and the see this group D E H K R, D E H is not there, right. So, 1 2 3, 3 into 2 equal to minus 6, and then what else we have? A C G M Y, this is 1, this is 2, this is equal to 3, L equal to 1, that is 2. So, total value equal to minus 4. So, we take the second equation, this sequence, and apply same equation here, right. This equal to this 4 is the total value. If you want the average, 4 divided by 2 3 4 5 6 7 8 9 10, this equal to minus 0.4. We take the second sequence, here how many times A? 1 2 3, L 2, Y M 1 2 3, and V 1, right. So, now if you see this A C G M Y, A C G M Y, okay, 3 6 7, 7 into 1, this equal to 7, right, 7 multiplied by 1 equal to 7, and then L and V are 2. So, 2 plus 1 3, 3 multiplied by 2 equal to 6, this will be 13, total 13. So, average equal to 1.3, right, 1 2 3 4 5 6 7 8 9 10, right, 1.3. So, you have two sequences, one sequence is minus 0.4, one sequence 1.3. So, what can we infer from these values? Second sequence is more hydrophobic than the first sequence, right. So, we have some sort of proteins which are prefer to be highly hydrophobic environment, for example transmembrane helical proteins. So, if you have some sequences which are predominantly hydrophobic, then you can see that protein could be a transmembrane protein. So, likewise, if you have different sequences, you calculate various features, not just hydrophobicity, various features you can calculate, and then you can compare with respect to the different features and see whether you can get the function of any particular protein. If it is completely not annotated, you can see this could be probably a transmembrane protein or DNA binding protein, or what are the probable functions and so on. So, in this case, you can, these properties will be very useful. You can get all the information from the sequence. We do not need a structure, from the sequence you can calculate these things.